If you're only familiar with organic chemistry or main group elements, then coordination complex chemistry can be a bit unfamiliar. There is, however, a shortcut called crystal field theory. The idea is based on considering the ligands as point charges and considering whether or not the d orbitals of the metal point towards the point charges. It works for an astonishing number of compounds, but sometimes you also have to consider the orbitals of the ligands, which is a different theory called ligand field theory. In this video, I'll go through the standard approach for determining crystal field splitting diagrams of coordination complexes. First, you need to determine the number of d electrons the transition metal has. This is easily done by taking the group number minus the oxidation state. So for example, ferrocyanide has iron in its +3 state, meaning it has 5 d electrons, written as d5. Then you should determine the possible shapes for the coordination complex. When you have 6 ligands, it's almost always octahedral, but it can be trigonal prismatic as well. 5 ligands can be square pyramidal or trigonal bipyramidal. 4 ligands can either be tetrahedral or square planar. 3 ligands is rare, but when it happens, it's almost always trigonal planar. 2 ligands is also rare, but when it happens, it's almost always linear. Each of these shapes have their own point groups as well, written in the parentheses. Next, you determine the splitting diagram for the metal d orbitals. Remembering where the d orbitals point, and based on the octahedral splitting diagram, you can determine the splitting diagram by evaluating how much the orbitals are pointing towards the ligands. If a d orbital is pointing towards a ligand, its energy will be higher. If we look at the octahedral splitting diagram and look at the geometry of a general octahedral coordination complex, we can see where the diagram comes from. The two orbitals higher in energy stem from the two orbitals that point directly towards some of the ligands. That's the z squared and the x squared minus y squared. While the three orbitals lower in energy are between each of the ligands. That's the xz, the yz, and the xy. When orbitals are equal in energy, they're called degenerate. So in this case, we have two degenerate orbitals higher in energy, and three orbitals degenerate to each other lower in energy. Orbitals can also be described using mathematical terms. Doubly degenerate orbitals are denoted as E, while triply degenerate are denoted as T. Now, some important terminology of crystal field theory. The energy splitting the two groups of orbitals for an octahedral complex is called delta O. For a tetrahedral complex, it's denoted as delta T, but in general, delta will be the energy splitting the highest and lowest orbitals. Delta will be a function of multiple variables, which we will go through. The first variable are the ligands. Ligands can be strong or weak field ligands. Strong field ligands interact more strongly with the orbitals, resulting in a bigger splitting. Weak field ligands interact less strongly with orbitals, resulting in smaller splitting. Strong and weak field ligands are sorted in the spectrochemical series. The strongest ligands are things such as the cyano group, then things such as triphenylphosphine, sulfur ligands, amines, water, etc. The series is made by measuring the delta O splitting through spectral measuring. Ligand strength is vaguely related to their nucleophilicity and basicity. Ligands aren't only sorted into strong and weak field ligands as well, there are some that are sort of in the middle. Now we can start determining the electron distribution among the orbitals. Most often, the distribution follows either one of two configurations, high and low spin. If the splitting is high, meaning delta is large, then the electrons will configure along a low spin configuration. This means electrons start pairing before they fill the higher energy orbitals. One such example is ferrocyanide. Here we have a D5 metal, it has an octahedral shape, and since cyanide is a strong ligand, we have low spin. So we fill the bottom orbitals, and instead of filling unpaired electrons in their higher degenerate orbitals, we pair the final two in the degenerate orbitals lower in energy. If the splitting is small, meaning we have a small delta, then that's better with the high spin configuration, which means it is more beneficial for the electrons to occupy the higher energy orbitals before they pair in the lower ones, such as in hexachloroferrate. The spin number for these complexes are 5/2 for high spin and 1/2 for low spin. The next variable for the delta is the point group, which then makes it important in determining whether it's a low spin or high spin complex. The point group is determined by the shapes we previously saw, and depending on how many electrons the complex has, you're able to see if the complex benefits from being high spin or low spin. For example, in the tetrahedral and square planar shapes, Let's assume we have a d5 complex whose electrons need to be distributed. Since the delta T is generally really small, it's common that it's a high spin complex. The square planar complex, however, has to put the electron all the way in the x squared minus y squared orbital, which is significantly higher in energy, meaning in all likeliness it's a low spin complex instead. Then finally, the delta and whether or not it's a high spin or low spin complex is depending on what metal it is. Metals using the 4d and 5d orbitals are almost always low spin because the orbitals stick out so much that their interactions with the ligands are very high, even with weak ligands, causing a large splitting. The result is that metals in period 5 and 6 are almost always low spin. Let's look at an example. Hexafluoroaurate 1- is an unusual complex with gold in a +5 oxidation state. The metal is D6, its shape is octahedral, and the ligands are weak. Thus far, it sounds like it should be a high spin complex. However, because gold is using its 5d orbital for the electrons, the interactions between ligands and orbitals is large, and thus the splitting is also large and a low spin complex is more beneficial.